Good morning. This is Sherry Kraber. Before we get started here, I'd just like to do a sound check. So if you would raise your hand if you can hear me, I would greatly appreciate it. Thank you, Ken and Jesse, Praveen. Great. Thank you so much. Today's webinar is a 1-hour crash course on design of experiments. And I hope in this hour simply to give you a taste of what DOE is and motivate you to use it for solving some of your problems. To prevent audio disruptions, we're going to keep the attendees muted. You can post your questions in the question area. If they are not addressed during the webinar, I will reply to you via email afterwards. If you have questions later on, you can also send them to stathelp@statease.com, and our team will certainly be happy to answer them for you. The slides that I'm showing here and a recording of this webinar will be posted on the webinars page of the StatEase website within a day or two. So StatEase was founded back in 1985. And our focus has always been on design of experiments with our Design Expert software. We just released version 13 in January, and I will be using that today. And our premier DOE training. The agenda for today is going to consist of talking about what is design of experiments. And then we will focus in on just the two-level factorial designs, kind of give you an overview of those, and really supplement this with a case study. So over half of the class will be looking at and using Design Expert software and showing you, kind of how to build and analyze a factorial design, at least at a rather high level without going into all the details. And then we'll wrap up the class. So traditional experimentation can be kind of pictured like this. We are often in our laboratory or our production process, and we just kind of say, I wonder what happens if I change this variable. What if I move this knob or dial, or change this input level? And so we do that, we make the change, and then we say, oh, I wonder what happens if I change this other thing. And we change this third thing, this fourth thing. And we do a lot of what's called one factor at a time experimentation. In contrast, designed experiments allow us to say, well, let's organize our experimentation, think about all the things that we want to do, and create a multi-factor statistical test plan that's going to give us the information about many things all at once. It provides us with the maximum information in the minimum number of runs. And, guys like Sir Ronald Fisher and George Box and Dr. Benken and all of these people have figured out matrices that are statistically sound, that will give us the information that we're seeking in as few runs as is reasonable to do. So it's really, really important with designed experiments that we actually do follow these plans and don't just try to create it ourselves, because we as human beings are unlikely to come up with something that is as efficient as what these guys have already done. And of course, there are things like optimal designs and stuff. There are computer-generated designs that follow the same principles. So using either designated test plans or software to build the design ahead of time is really, really an important step. design of experiments is making a very, very systematic series of tests. We are making changes to our input factors on purpose, and we are measuring the responses or the output information, and we are trying to establish a cause and effect relationship, a data-based relationship between the factors and the responses. This relationship goes above and beyond the fact that your process probably has noise in it. It probably has just uncontrollable things like temperature variations, humidity variations, chemical degradations, that occur over time. And so that makes it even more important to do a statistical experiment so that we can properly account for that noise in the process and still be able to correctly identify the relationship between the factors and the responses. So in this slide deck, I have a couple slides here of vocabulary, so you can go back and refer to these. But the controllable factors are simply your inputs that can be changed during the experiment. These may be either numeric or they might be categoric. So numeric would be something like time and temperature that operates on a continuous scale. Categoric might be something like vendor, the raw material vendor. It could also be something like a color, black versus yellow, or other things that are kind of names. Uncontrollable factors are the things that might fluctuate during the experiment, as I've mentioned. And then your responses, your Ys, are the measurable numeric outputs of the process. Yield, tensile strength, efficacy of the drug, things like this. There are millions of different types of measurements that can be done. Ideally, they are numeric, and less ideally, there's something like pass, fail, or some sort of rating system or something. We can do all sorts of things. The outputs cannot be categoric. Okay, so we often think of designs. We often think of experimentation in one factor at a time. So I'm recalling a situation where a group really only knew about one factor at a time. And their current process gave them results here of 17. They were trying to change a variety of variables to find a way that they could at least double that output response. So if they're at 17, they're looking for responses of maybe 34 or so. So they tried changing factor A. And so if we go from this corner, the standard A, and we change A, go up to a different setting for A, the result they found was a 25. So a nice improvement, but not as much as they were hoping for. So they tried changing factor B. Again, this lower corner is the starting point. If they change B, they went up here and they found results of maybe a 26. Again, a good improvement, but not as much as they're hoping for. Changing factor C resulted in actually basically no improvement whatsoever. So they were scratching their heads and trying to figure out what they were going to do. They had a new engineer come in, and he said, well, in school, I learned about this design of experiments. Should we put these factors into a DOE test plan and tried completing all of these runs. Well, I mean, to be honest, they kind of poo-pooed him and said, no, that DOE stuff, that doesn't work for us. We've never had any success with it. But he kind of kept at them and said, you know, you're not having any success with what you're doing, so why don't we try the DOE? Eventually, they caved in and said, okay, you go over to your corner and you can do the work that you want to do, and just don't bother us. So he did. He went over and he ran this complete two-level factorial design. And as you can see, there are some combinations of these same variables that they were studying that resulted in not just a 2-time, but a 4 to 8 time increase in the response. So he had some huge successes, and they said, well, wow, what are you doing? And he said, well, that's because I tried some conditions, some combinations like the new A and the new B together, and even with the new C level together, that gave us some better response values than just any one of them on its own. So the interactions of these variables produced some better results than any one at a time. So they would never have found this via just one factor at a time studies. So traditionally, we study one factor at a time, holding everything else constant. This is very easy for our brains to process. We can just think about things one at a time. But it doesn't account for the interactions, these combinations of factors. In long-term testing strategy, it's serial processing. It's very, very inefficient. With the factorial design, the advantage of it is that we can study multiple factors changing at once. Now, the downside is that our brains can't handle the math behind this, but our brains don't have to. That's why we have software. You know, this is the 2020s, and we have great software programs that take care of the statistics, take care of that math, and can analyze the data for us. They can figure out the interactions between the variables. And this will actually maximize the information that you get in the fewest number of runs. So design of experiments is an umbrella. The words are kind of get confused sometimes, but actually design of experiments is this overarching umbrella. And underneath this, there are different types of DOEs that we can run. So we can run factorial designs, response surface designs, mixture designs. These are all types of DOE. So the one we're going to focus on today is a factorial design that allows us to get information about the main effects and interactions. We might keep the number of runs small and just do a screening design to get just the main effects, or we might do a little bit bigger design that fully characterizes and adds the interaction information in. 2 levels for each factor allows us to keep the number of runs as low as possible. Response surface designs allow you to build quadratic or cubic or higher order polynomials that actually model non-linear factor and response relationships. So if you know that you have a non-linear relationship between the variables and the outputs, then response surface would be the correct tool to use. Every factor is set at 3 or more levels. So this requires more runs, but it also provides more information, more complete polynomials. For those of you who are working in formulation, if you are studying formulation, so you might be in the pharmaceutical industry or the food industry, where you're working with recipes, or oil and gas, or other chemical and maybe even biological situations, maybe you're working with media, then you want to look at mixture designs. These are a type of response surface designs where we model the formulations that where the responses are dependent on the proportions of the mixture components. And the mixture designs are required to properly model the dependencies between the components. You get this triangular space rather than a cubic type of space. If you are interested in learning more about that, on April 14th, we're having a crash course in mixture DOE webinar, another one hour webinar that will more fully explain this. That webinar is also recorded. We did it a couple months ago, so it is available on demand if you don't want to wait until April 14th. All right, let's dig into two-level factorials just a little bit. A two-level factorial means that each factor is set to two levels, a low level and a high level. These are coded or represented as a minus, -1, and a +1. And we, for each, for the design, we run all combinations of the 2, 3, or 4 factors. So with just 2 factors, it looks like this, where you have the low A level combined with the low B, and then you have the high A combined with the low B, and then you go back to a low A and combine it with the high B, and you do the high A and high B. So all possible combinations. With this structure, we can calculate the effect of going from low to high A by averaging the information at the runs where A is set to its high level, and we average the runs where A is set to its low level, and we take the difference. That's this whole formula here, and that will give us the effect of A. To get the effect of B, we average the runs where B is set to its high level, that's runs 3 and 4, and average the runs where B is set to its low level, that's runs 1 and 2, take the difference, and that will be the effect of B. And this would go on and on if you had 3 factors or more. We usually write this out as a matrix in any software program. It's going to give you the matrix. We just show you the matrix for the main effects in the software, but hidden behind the scenes is the rest of the design layout, the rest of the matrix, and that's going to include the interactions. So for instance, you'll have a column for the AB, the AC, the BC, and even the 3-factor ABC interaction. For these 8 runs here, you're going to be able to calculate 7 independent effects plus the average, the overall average. So you get 3 main effects and 4 interactions. Let's see. And, you know, if you were trying to manually calculate the effects, you could look at this matrix, and for factor A, you would find the responses where A was set to its high level. There's 4 of them. Average those, and then average all the runs where A was set to its low level, and take the difference, and that would give you the overall effect of A. Likewise for all the rest of the columns. In a full factorial design, all of these columns of information are unique. So the two-level factorial design has a very simple structure. You could create that by hand as long as you're doing a full factorial. If you have a lot of factors and you want to do a fractional factorial, then I would let software do it so it can give you the best structure. But those require the minimum number of runs. These designs have hidden replication, which gives more power to detect effects than 1 factor at a time studies, and ultimately test more combinations. So as you saw in that first example, that company was able to, because they tested more combinations, they found areas that worked a lot better than the 1 at a time combinations. So the two-level designs reveal the interactions, which are often the key to new discoveries. They are, easy to analyze, and we'll use graphs. I'm going to show you the graphs at the end here to interpret the results. Two-level factorials also form the base for some response surface methods, specifically a central composite design, but also some other designs. So you can start with a two-level factorial, and if you're getting good results but you want more information, then you can augment them straight into a central composite design. In Design Expert, when you open up the software, you're going to see a grid, and it's a color-coded grid, and the color coding has specific meanings. All of the white squares are the full factorial designs. So you can see we have 3 factors in 8 runs, or 4 factors in 16 runs. And then the green designs, green means go, it's the best, are going to give you the main effects and your 2-factor interactions. So basically all the information that you really, really need are included in the green design. So those are the ones I recommend first. The yellow designs, yellow usually means caution. They're going to give you clean main effects, so they will correctly estimate all your main effects. And these main effects will not be biased by 2-factor interactions that are kind of hidden that you're not looking for. So that they will be really good information on the main effects. The red designs, some people tend to go to those because they're so small. There are problems with those. Although they look like they'll give you main effects, in reality, those main effect estimates are biased if any 2-factor interactions exist in your process. I sometimes hear people say, oh, but I'm not looking for 2-factor interactions, so I could just use a red design. You know what? It doesn't matter if you're looking for it or not. If it exists in your process, then it's there, and it will bias these red designs if 2-factor interactions even exist. Whereas the yellow designs give you unbiased or clean main effect information. All right, so we're going to jump into using Design Expert software by looking at a case study. This case study is actually a tutorial. It is found in the Design Expert help system. So just look for the TwoLevel Factorial filtration rate tutorial, and when I'm done, you can open that up and you can walk through a complete, probably even more in-depth than what I'm going to go through today in this quick webinar. So you can duplicate this. The data file is there in the help system. So go ahead and look at that afterwards. The case study comes from Doug Montgomery. He is a professor at Arizona State University. And it comes from a job that he did for a manufacturer of the siding, wafer board, that is put into mobile homes, trailer homes. Now, this was done back in the 1970s, and at that time, in their process of using a glue, they used formaldehyde in the glue, which, today we realize that that's not really a good product to use, but they used it to help with the filtering of the glue. It made it flow better and faster, but it also smelled bad. So they wanted to find process conditions that reduced the concentration of the formaldehyde that they were using, so they wanted to use less of it, but also gave them a high filtration rate. So whatever they could do to speed up production and also reduce the amount of the formaldehyde would be a win-win for this manufacturer. The 4 factors that they're going to study in a 16-run design are laid out here: temperature, pressure, concentration, and stir rate. And this concentration was the formaldehyde. They were currently using a 4% concentration. They were trying to find out if they could go down to this 2% concentration. So going from 4% to 2%, but also looking for combinations perhaps that could give them a higher filtration rate, which was the response. I'm not going to spend any time talking about power of a design, but other than the fact that it is basically the ability of the design to detect an effect of a certain size. We have other webinars that go into this concept of power. The data spreadsheet is going to look like this with the gallons per hour. So you can see we've got data all the way from about 40, in the mid 40s gallons per hour, all the way up to over 100 gallons per hour. So a nice spread of the data. I'm going to open up the software next, but just to show you what we're going to do to analyze it, we're going to look at some effects plots to choose the significant effects. Then we're going to review the analysis of variance. Then we're going to look at the diagnostics. And finally, we're going to look at the model graphs. So let me get Design Expert open. And I'm just going to kind of walk through that build process. So this is usually your opening screen. And so we chose that 4-factor in 12-run design. It's a full factorial. And we click next, and you have to enter all of your factor names. And you have to choose ranges for each of your factors. A low and a high range that are far enough apart that you would expect to see a difference in the response. You have to be able to change the response if you're going to detect a change in the response. All right, then the next page allows you to enter your response name, and you could have lots of responses. We're just looking at one here, but you can certainly have more than one. And the software gives you a power, and then it builds the design for you. At which point you have to go out and physically run these experiments and then type in the data. So let me get this open again with the data. All right, so in Design Expert software, the first part of the software gives you information about the design. So there's some basics, a little summary about that design. There's a graph columns where you can do a scatter plot of any factors or responses against each other. There's design evaluation. This has nothing to do with data analysis, but it's evaluating the design. And then the second part is the actual analysis. So I'm going to click here on my response name, filtration rate, and I'm going to click on Start Analysis. Okay, so two-level factorials are kind of unique in that when they don't have any replication, building an ANOVA, the analysis of variance, is just a little bit more complicated. We have to tell the computer which terms we want to be in the model and which terms we want left behind. You always need some terms left behind to be in the residual. So you have to build these F-tests. An F-test has something in the model and something in the residual. So you want the terms that look like they're probably most significant to be in that numerator. And then you want the terms that look like they're just part of the noise to be in the denominator. So the easiest way to do that is to just put all the effect estimates into a half normal plot. This is a plot where we test for normality. And the deal is that the terms that follow a normal distribution are going to fall on a straight line that starts at 0 and goes up. So all of these terms that are on the straight line are the ones that are not statistically significant. We want to leave those alone. We want to leave them to be our test, the denominator of our test. In the numerator, we want to select the terms that are jumping off the line. These are the big effects. If you look at the x-axis down here, it goes from 0 to 21. And so the bigger the effect, the more likely it is to be significant. So we can select effects, and basically we are turning them on and putting them in the numerator of our ANOVA. So I have all of those selected. They're also big here on the Pareto chart. And then I can click on ANOVA, and it's going to build based on these selections. Okay, so my ANOVA now has those 5 things in the model, and the other 10 things are pooled together and are in the residual. And this allows us to do all of our F-tests and calculate all the p-values. So that's just a key difference between analyzing a 2-level factorial and analyzing a response surface design where replicates were included and you just have more information to create your ANOVA. You have to use that half normal plot. Okay, so the ANOVA should contain only things in the model that are statistically significant or that are required to maintain model hierarchy, which is kind of an extra thing. That would say like model hierarchy means that since I have AC as significant, then I also want the parent terms A and C to be included in the model, which they are here. And for AD, we want the parent terms A and D included in the model. Even if they were not significant, we would still include them in the model. Okay, so that's just the very, very basics of the ANOVA, watching your p-values to make sure that they are probably less than 0.05. That's just a general guideline. Then some other statistics that you can also look at would be the R-squared values, especially focusing on the adjusted and predicted R-squared, that in order to have good predictions, you want these to be higher. There's no specific cutoff, but higher is better than lower for making predictions. And basically saying how much of the variation in the data is being explained by the model. Okay, so there's guidance down here for you. Now, all of this ANOVA is predicated on some statistical assumptions that are summarized in the diagnostic plots. So after you've looked at the ANOVA, then you go to the diagnostics and just verify a few things. And these are summed up in the help system and in other webinars. There's also a handbook for experimenters that if you purchase the software and register the software, then you can get the handbook for experimenters as a download. So that's a good idea to do that. The normal plot of the residuals should show that the data is normally distributed, that the residuals are normally distributed, to clarify that. The residuals versus predicted should also be just a nice random scatter, as it is here. No trends, no increasing plots, and the residuals versus run also should show no trends, just random scatter. No points outside these red lines. You know, you can look for outliers here. So we don't have any outliers. This is great. And then finally, look at the Box-Cox plot. It will tell you if you need a transformation or not. You don't have to worry about understanding the plot. We explain that in our classes. But what you do have to do is read the recommendation. Recommended transform, none. As long as it says none, then you're good to go. If it would say you need a log transform or a square root transform or something like that, then you would actually have to go back to the beginning and apply whatever transformation it told you to do. So we're not doing anything. We don't have to reanalyze or anything, but just read the recommendation. Okay, once you have validated the ANOVA and made sure all the diagnostics look reasonable, they don't have to be perfect, but they should be reasonable. Then you should go to the model graphs, and this is where the fun starts. Now we can start learning how to understand these various graphs, starting with just one-factor graphs. You know, I can do one factors of all the factors. So here's the one-factor graph of A. Overall, as you increase temperature, you increase the filtration rate. B was not statistically significant. C, again, it has an upward trend, and also D. But if you notice that each of them has a warning. Well, the B's warning just says it's not in the model, but the other warnings say the factors are involved in interactions. That means that this graph by itself is not sufficient. Looking at the one-factor graphs is not going to give you the information that you need. You have to look at the interactions. So we'll start with this AC interaction. Okay, so on the bottom, on the x-axis, is factor A, temperature going from 24 to 35. On the y-axis is the filtration rate, gallons per hour. We're trying to increase the filtration rate. The second factor, concentration, is actually shown as two lines, and you're going to have to read the legend in order to figure out which line is which. The low level is always the black line, and the high level is always the red line. So the black line is at 2% concentration of formaldehyde, and the red line is the 4% concentration. If you remember the original goal, we were trying to increase filtration rate, and we were also trying to use the lower amount of formaldehyde. So the black line was desirable. So this is good. It's showing us some good results. If we are up here at this point, that's the higher temperature, but it's also the lower concentration. It's the 2% concentration. Okay, so this point is good. By the way, these bars are called LSD bars, or least significant difference bars. And they are kind of showing you the range of the average. So the average under multiple experiments might float in that range. And when those LSD bars are separated, they are not overlapping, then you can say that those two means are statistically different. Now, if you look at this LSD bar and this one, those are actually overlapping. That means that there's not a statistically significant difference between temperature at 24 and temperature at 35 when you are operating at the 4% concentration. Okay, I'm going to come back to that statement in just a few minutes. In the meantime, we like this low value of concentration. Let's switch to the second interaction graph. So what I'm going to do is go to my term list here. It says AC. I'm going to switch it to the AD graph. And of course, I could also just right-click on these and change what's set to the X1 and X2. So this is the AD graph, but right now concentration is set at its mid-level. I'm also going to move concentration down to the low because on the other graph, I just found out that I really like that. And so you can see if I move concentration down, it moves that graph. Okay, so this is the picture that I want to look at because now concentration is set low. And now I can focus on the temperature and the stir rate. Again, the two lines, the stir rate is set to 10 RPM at the black line and 30 RPM at the red line. So if we are trying to maximize filtration rate, then we would be looking at the values up here, the, again, high temperature and high stir rate, combined with the low concentration of formaldehyde. Okay, so all of these in combination kind of gives you your final settings for this factorial design. Now, there are plenty of other ways of looking at these. I'll just, kind of glance at them. They're just alternative ways of displaying the data. You have these contour plots that show the two factors on the X and Y axis, and then the filtration rate is in the middle. So this is like I'm going from 50 gallons per hour to 60 to 70 to 80. You can see how it's increasing. It's like a topographical map of mountains or hills. So often I like to look at this in 3D so I can kind of see that. So this is the same graph, and I can see how it's increasing as I'm going in that direction. So we use these graphs usually more in response surface methods when we have more complex polynomials that we have to show the shape of. But I'd show that briefly. And then a Q plot is also a real simple way of displaying all the information. So that would be an alternative. This is A, C, and D, so the three factors that are significant are all put on here. So I can see that up here in this corner, which is the high A, high temperature, high stir rate, combined with the low concentration, is the highest filtration rate available. Okay. Now, there are other ways. There are optimization techniques that we can also use to find our optimum. I would always recommend looking at the graphs and learning as much as you can from the graphs. But under optimization, you can also set a goal for the filtration rate. We want to maximize that. Here's a key thing, though, that most people don't realize they should do, is that we want to maximize filtration rate, but the default setting is to use the range of filtration rate that you got in your experiment. usually people don't actually want their final results to have filtration rates this low. We might want this to actually be focused on filtration rates that are at least 80 and maybe up to 110. Maybe we can find some region that would predict even higher than where we're at. So modify your lower and upper limits to reflect your true desires for the system. The other thing I want to do in this case is I want to minimize the concentration. Now, since this is a factor, I do want solutions to span the entire range of concentration that I studied, so I'm not going to change the range for concentration because that's a factor, but I do want to change the range for the response. So now I have two things that I'm searching for, and optimization finds the same results that we found graphically with high temperature, low concentration, and the high stir rate, giving us a filtration rate of 100.625. So with one response, you should be able to do this graphically, but when you have 2, 3, or 10 different responses, then you analyze each response, get a model for every response, and then you can use optimization to kind of find your overall optimum, your overall best set of conditions. Okay, so let me flip back to the PowerPoint presentation here and review a couple more points. And you will be able to download these slides after the session today. This shows that the effective temperature depends on the formulation, the concentration of formaldehyde. So if my temperature is low, then filtration rate would either be low or it can be higher, depending on whether I have 2% or 4% formaldehyde. And if temperature is high, then it actually swaps. That's why this is an interaction effect. The effect of temperature depends on the concentration of formaldehyde. And same with the other thing, you know, the effect of temperature also depends on the effect of on the setting of stir rate. All right, now there's a key discovery here. One factor at a time. If we had, you know, taken this back to our original team and asked them to think about what factors they would have studied, temperature probably would have been rejected as a factor to study because at the original 4% formaldehyde concentration, there was no temperature effect. How do we see that? That was right here. At the original 4% formaldehyde concentration, if you went from 24 to 35 degrees, your filtration rate hardly changed at all. It was, you know, that change is probably just buried in the noise of the process. So the original experimenters could easily have just said, oh, you know, we don't have to worry about temperature. We can just keep that fixed. And that would have been a fatal, fatal flaw because the factorial DOE discovered that temperature has a significant interaction with both concentration and stir rate. So, you know, that's why you want to, you know, really include potentially critical factors in your designed experiment and see how they interact with other things. And don't let your biases coming into the design, you know, affect you too much when choosing the factor settings, the factors to study. So we get the new maximum, we get a DOE success with this combination of the low formaldehyde, high temperature, and high stir rate. All right, so let me just wrap up with a few final slides. And if you have questions, you are free to type them in to the question box, and I should have time for a few questions. We want to, trim out the one factor at a time studies. You can really gain a lot in your manufacturing development, your research R&D by using factorial designs for detecting effects, response surface designs for that real critical optimization, and if you're dealing with formulations, then use mixture design. And Design Expert is just a very intuitive and very powerful program to use. So, of course, I'm going to encourage you to consider using it. If you want to take the next steps in learning more about design of experiments, then I would encourage you to register for one of our workshops. The Modern DOE for Process Optimization covers both factorial and response surface designs. And then the mixture class covers everything you need to know for doing DOE with formulations. We have public classes that work great for individuals, and then we can offer private classes if you have a team of 6 or more. And this would allow you to customize the class a little bit more to specifically meet your needs. We will be starting live in-person on-site training again this May or June as we start to open up here in the US. So if you are interested in on-site training, definitely please contact us and we'll be happy to talk to you about that. Otherwise, our distance learning training is here to stay, so that will remain available as live distance learning options for years to come. Now that we are into doing it, we will continue with that. We have some awesome textbooks. They're available online. You can go to Amazon or the Taylor and Francis Productivity Press websites. Just Google for these books. You can get them in softcover, or you can get them as ebooks, and you can either buy or rent. So they are available in many, many different versions. Okay, so somebody asked, how do we choose whether you do a two-level factorial or a response surface design? So going back to, in fact, I'm just going to do this like this. I'm going to save now. One thing I would encourage you to use is at the very beginning, there is a design wizard. This wizard will actually help you make that decision. It asks, what is the purpose of your design? And if you're not sure what these mean, just click on them. So you're going to click on all of them and read the information and decide what you can do. So maybe if I want optimization, then it says, okay, what type of design do you need? If I want continuous factors, I would choose this one. Do you have any hard to change? I'm going to say no. And then what type of factors do you have? I'm going to say I have all numeric factors. Then how many factors do you have? And you can play with this. Maybe I have 5 factors and I can do 30 runs. Then it would recommend a particular type of design. If I can bump this up to 32 runs or 36 runs, maybe there are other options. How about we reduce it to 24? If I say I only have 24 runs, then it gives me a couple of options, but it says, this has more runs than you've entered, or this design is insufficient for optimization, but that might be what you want to do. So that design wizard is a great way of deciding, giving you a starting point, which design is best for me. In general, if you are restricted on the number of runs, then the two-level factorials are going to be the starting point for you. If you have a bigger budget and you want to do full optimization and you think that the relationship is nonlinear, you think you might need a quadratic polynomial, then you need to go to the response surface designs, that can be found here. Okay. Somebody asked how to choose the alpha value in a response surface, like a central composite design. I am going to direct you to a different set of webinars that I ran last month. I ran how to build a response surface design and how to analyze a response surface design. So those two are both recorded. You can look them up and they will answer all your questions about the response surface designs. Is a factorial design the same as randomization? Well, randomized, so underneath this factorial, we have randomized designs and we have split plot designs. Split plot designs have restrictions on the randomization, but otherwise, all of the designs, whether they are factorial or response surface, they're all going to be given to you in a randomized order. So if I just take this design and build it, go to finish, it's giving you the runs in a randomized order, which is how you should run them. That is statistically sound. That's actually one of the ANOVA assumptions too, that we do assume you are running these designs in random order. All right, that is all the time I'm going to have for questions today. If you do have more questions, you are welcome to email them to stathelp@staties.com or to myself. We will put these slides and the recording up on our website as soon as we can. And so with that, I would like to just say thank you for attending, and I wish you a very good day. Thank you very much.